has magnetic smith, or like that could have flowers, something like that. Oh, really? So like, still the first seven. I still need flowers. So yeah. I don't need this one. Yeah. And the two, other than like this one, the clown, the other one is like. Yeah. Oh no, I just started reading. Yeah, it's easy to I use that archie before. But I like that. Yeah.
Alrighty, so let's start. So I post this file yesterday night in Canvas. So you go to the chapter 5 slides, and there is this document, Word document. So this is the exam review for Wednesday. So I put here calculate the oxidation number of manganese in KMnO4. So if you know how to solve this problem, you will know how to solve this kind of problem. I will not put KMnO4. I might put KCr2O7, or I might put ZnO2 or something like that. Yeah. So just look the slides and you know how to solve that problem. Make sense? So this is not an exam problem. So if you know how to solve this, you know how to solve other. So this kind of problem we already solved in the slides. So go back and do that. Yeah. And the following reaction is oxidation reduction reaction. So which one is oxidized here? So Zn is going from 0 to +2. So that's oxidized, right? So which one is reduced? So this guy is jumping down from +2 to 0. So this is reducing, right? So this kind of thing. Again, this is not the question, yeah? So this is just, if you know how to solve this question, you will know how to solve all other questions, yeah? So like that. And which is oxidizing agent? So something is reduced is called oxidizing agent. So this is being reduced. So jumping from +2 to 0. So +2 to 0, right? So this is reduced. So something is reduced is oxidizing agent. So CO2 plus is oxidizing agent. Yeah. So we practice this kind of problem. So look the definition, which statement are correct. Loss of electron is oxidation. So this is correct. Gain of electron and the loss of, if something throw the electron, it is called oxidation. If something take the electron, that's called reduction. So something like that. Look the following answer and calculate which one is a limiting reagent. So do the mole to mole ratio, and which is more, that's excess reagent, which is less, that's limiting reagent, right? So and look here. So This is a milliliter. And we need to convert this milliliter to liter, and this is a molarity. When you have a molarity and milliliter, that converted to liter, you can easily calculate the number of moles. Yeah, something like that. And then when you have a moles, you can convert that into grams, right? So like that. So all these are either the problem in homework or they are in the slide item. Yeah. So here is the dilution problem. For dilution, we always use this formula V1M1 equals to V2M2. If there is a titration problem, you may want to say it's a 1-to-1. This reaction is 1-to-1. So V1M1 is equals to V2M2 works here. So this is not 1-to-1. So this is a 1-to-5. So this is 1-to-5. So V1M1 by 1 is equals to V2M2 by 5. Works in this case, right? So you can go there. Yeah, something like this. So just practice this. So I will hold the office hour in next Tuesday, sometime between 10:30 to 11:30. And if you cannot solve this problem, you can write there and we talk. Yeah. So let's see here. The cylinder put in oven, it gives us 1000 joule of heat energy. If gas expands to produce 200 joule, how much heat is used to change the internal energy? So this is the income, 1000. So this one 200, and you are your expenditure. So income minus one expenditure is equals to another expenditure, right? You can easily calculate. So basically, I told you if you use this formula, always it works. D plus dW. So what is given? dQ is given. You need to calculate d. So this is 1000. So this is your income. du. You don't know how much is used to change the temperature of the heat. How much heat is used to change the temperature of the gas? dW. The work that is given 200. So you are going to calculate this one, right? Easy. So 1000 minus 200 is d, right? That much used to change the internal energy. So let's go through this problem, and I think this will be fine. So we'll see what happens. Yeah. So let's continue our lecture here. So we were doing this kind of thing. So I told you for the coffee cup calorimeter, you will surely see one question in coffee. Yes.
The test is on Kansas, right?
Yes.
So then do we still have lecture that Wednesday still?
Yeah, I think we do.
Okay.
Yeah. So the exam is just 1 hour. So for coffee cup calorimeter, you are going to use this equation MC T2 minus T1. So T1 is before you mix the temperature. T2 is after you mix and shake the material. What is the temperature? And the mass is the mass of water plus whatever you put there. Mass of, if you put NaOH, mass of water and NaOH. If you put HCl, water and HCl. Whatever you put there, so you need to take all mass. Yeah. So that one is that one. And C is a specific heat capacity of water, that is 4.1. So just do the calculation, whatever number comes here, that is the amount of heat produced inside that coffee cup calorimeter by doing the reaction. Have you got that? So this will be the exam. So yeah, so you just use Q equals to MC T2 minus T1. It's not because it is simple. It's not I'm going to put this in exam because it is simple or it is hard. I'm going to put this in exam because it is important. Yeah. So all thermodynamics is based on this one. So like that. So here, let's do one problem here. So this problem is saying it's a coffee cup calorimeter problem. So you put 6.50 gram of solid sodium hydroxide. So you have a coffee cup here, coffee cup. So 2 coffee cup here. So how much sodium hydroxide you put there? That is 6.50 grams. So put 6.50 gram here, sodium hydroxide, and how much is water? 100 gram water. So it is already 100 gram water, 100 gram water, and you cover this with the cap, and you are looking the temperature change here. So temperature change is how much? Temperature change is from 21.6 to 37.8. So that's T2 minus T1, right? So what is the heat produced here? So Q is equals to MC T2 minus T1. So M is 100 plus 6.5. So we need to add both number there, because when we mix sodium hydroxide or anything in water, their specific heat capacity really don't change. That's always 4.1. Yeah. So that's M is 100 there 6.5, C is 4.1. So temperature change from 21.6 to 37.8. So 37.8 minus 21.6. So just calculate this, whatever the amount of heat you get, that's the amount of heat it releases. Yeah, makes sense? So, and what is it asking here is calculate the delta as kilojoule per mole of NaOH. So that is the total amount of heat. So this joule is the total amount of heat. So, but this is asking in terms of kilojoule per mole. So whatever it needs, it comes here is that gives me 7212 joules, which is 7.2 kilojoule. 7.2 kilojoule, right? So joule converted to kilojoule, so you divide by 1000 and you get the 7.2 kilojoule, right? Now it is asking me from how much I got that that amount of heat, from 6.50 gram of 6.50 gram of sodium hydroxide. So it gives how much heat we got is 7.2 kilojoules. So 7.2 kilojoules. But it is asking how many kilojoules in 1 mole per mole heat I will get. So just convert this into moles. So 6.50 would be divided by 40 here. So sodium hydroxide is 40. 1 mole of sodium hydroxide is 40 gram. So if you divide 6.50 to cancel this gram and divide by 40, you would get 0.1625. So 6.50 is 0.1625. So basically, this guy is 0.1625 moles. Right? Make sense? So if 0.1625 moles gives this much heat, so the question is asking how much heat would you produce by reacting with 1 mole of NaOH. So we need to calculate that for 1 mole, right? Make sense? So now let's take the ratio and you can get the heat for 1 mole. So X divided by 7.2 is equals to 1 divided by 0.1625. So the 7.2 goes here, so X is equals to 7.2 here, and then divide by 0.1625. So this many kilojoules. Why kilojoules? Because 7.2 is a kilojoule, right? Simple. So 7.2 goes here, and 7.2 divided by 1625. So like that, yeah. Good. So if I might give a question that you may want to just stop here. So I would not ask you how much heat per mole NaOH give. So I just say, okay, calculate the amount of heat here. If I add 6.50 gram of sodium hydroxide in water and the temperature change from 20 to 75. Yeah. So you don't have to go up to that. How much heat would give by reacting 1 mole of NaOH. So like that. Yeah. So you just stop here. So if it is not asking what is the amount of heat per mole of NaOH, you don't have to calculate the 1 per 1 mole, right? You just calculate the amount of heat and you have. Good. So I mean, 7.2. So yeah, so all problems are like that. Just to practice yourself, so we can do all the problem here. So let's do another concept here. Hess's law. So this problem will be in exam, yeah. So copy of calorimeter, sure there will be one problem in exam. So let's look another concept here. So Hess's law. So Hess's law is basically no matter how many steps you do the reaction, the total heat change is same. So for example, I have something I am converting A to E. So I have a chemical here. So I want to convert this chemical A to chemical E by doing some reaction. Yeah. So I directly change from A to E here. This is one path. This is one route, right? I take the A and convert to E. So there is another way. So what is the heat change here going from A to E? I can denote that heat change is delta H delta S like that. So maybe this is 300 joule. When I convert A to E, maybe I get 300 joule, 400 joule, 500 joule. I don't know. Yeah. So like that. Make sense? So if it was water, yesterday we were talking about when hydrogen and oxygen is bonded, H2 plus O2, I would get water here, and the delta H was, I don't know, maybe 300, 400 joule here, something like that. So I can do this way. Or I can go from, I can make from A to E in multiple steps. So first I convert A to B, A to B, and I measure the heat change here. So let's say that's a delta H1. And then I convert B to C, and I convert how much heat is released when I did this reaction. So that heat I denote by delta H2, and then I go from convert C to another chemical D, and I measure the how much heat I change here during this reaction, delta S3, and I can convert the D to E by another reaction, and I measure the how much heat I change from going from here to here. So that's delta S4. Make sense? So we did two ways. So I directly convert from A to E one way, another way I did many steps, right? It's like you are traveling by plane here, you are traveling by car here, like that, yeah? So in many steps or in one step. Make sense? So like that. So what they did this kind of experiment, and they found that the delta, whatever the number comes here, that number, this one step number is equal to the sum of all the steps. So delta H1 plus delta H2 plus delta S3 plus delta H4. So this is called Hess's law. Make sense? Like that. So let's do one example. So what is the Hess's law say? The heat change by converting one chemical to another chemical in single step is equal to the sum of all the heat change if we do the same reaction in multiple steps. Yeah. So let's do the example, and then we'll better understand this one. So look here. So the methane is here. Here we are burning methane gas with oxygen and producing carbon dioxide and water. And when we do this one, when we burn methane, it gives 890 kilojoule per mole of heat energy out. So methane is a fuel. So when I burn that one, it gives large amount of heat to the room. So room becomes hot, right? So that minus sign says that the heat is being released to the room. So exothermic reaction. I can do the same reaction another way. First of all, I burn the methane with oxygen, and I'm not producing carbon dioxide. Look here, I'm just producing CO, carbon monoxide here, right? And then I produce 2 water, and then I produce half oxygen. And in this reaction, I get minus 607 kilojoule per mole. Now I take this system here. So this is this system CO, 2H2O, and half O2, and I allow it to burn further, and so I get CO2 and 2H2O. Look here, CO2 and 2H2O. So here from methane to CO2, 2H2O, I go directly in one step. Here I go from CS4 to CS4 2O2 to CO2 H2O in 2 steps. Make sense? You got that? So in first equation, I am directly burning everything and making carbon dioxide in water. In the second method, I am just doing the control oxidation. So I give a little bit oxygen, and I allow it to convert to carbon monoxide, and then I again put a little bit oxygen and allow it to burn that carbon monoxide, and I get carbon dioxide. Yeah, so 2 steps. So and look here. So here in the single step A to C directly, I have 890 joule. So the first 890 joule in the single step, and this sum the heat in 2 steps. So this is the first step. The heat change here is minus 607. Minus 607. This is the first step. And then in the second step, I have the heat change minus 283. Minus 283. So this is also joule, minus 283. So add this and this, and that's minus 890 joule, and this also minus 890. Make sense? So no matter how many steps you do the reaction from going from A to B, the net heat change is the same. Yeah. So it's just like some of you may be doing the SI leader. Some of you may be doing the tutoring, all right? Some of you just study yourself. You might be doing many steps for this course, right? So at the end, what will you do? You all will pass, right? So just like that, somebody done do many steps, also pass. Somebody does many steps, also pass. So they achieve the same goal. Yeah, the same. So the change in heat is the same. Make sense? Right. Good. So this is right here. So let's do one calculation here. So don't study this Hess's law for this exam. So I'm not going to put this in exam. Yeah. So our book, general chemistry basically covers all old chemistry, a little bit, everything. Yeah. So general chemistry is 2 months. So let's do this problem here. So here is a problem. This is saying calculate the heat change for this one. CS2 plus oxygen give carbon dioxide and sulfur dioxide. So this is the reaction, and 3 is there, 2 is there. So 3 here and 2 here, right? 2 SO2 here, 2 SO2 here. So like this. So what is the heat change? How much? So basically it is asking. So if I put the CS2 in coffee cup calorimeter and dump a lot of oxygen there and allow it to react, how much heat that MCT2 minus T1 would give me here, right? That's what it is asking. Make sense? The problem is that. And it is giving a number of steps here. So one way you could do this. So you have a carbon and you can bond with oxygen, and this is one step. In that step, you get carbon dioxide. Yeah, carbon dioxide here. And how much heat? So if you put a lot of carbon there and a lot of oxygen there, and you bond in coffee cup calorimeter, how much heat you would generate by using that Q is equal to MCT2 minus T1 equation. Yeah. So that's what it is. So the heat using that Q is equal to MCT2 minus T1 will be minus 393.5. Minus 393.5 kilojoule, right? Kilojoule per mole. So if you take 1 mole of carbon there, dump a lot of oxygen, allow the reaction to complete, and measure the temperature T1 and T2. Use Q is equal to MCT2 minus T1 formula, and how much heat you get, this much number you get. That makes sense? So another equation is like this: sulfur. So you did another equation another way. So another reaction: sulfur and oxygen gives sulfur dioxide. And if you do the same thing, how much heat it will give out? So minus 296.8. So this minus means heat is coming out from the reaction. Minus 296.8 kilojoule per mole. Now we have another equation here. Carbon plus 2s. So carbon plus 2s will give us by this reaction CS2 and CS2. Is it a plus or minus? So this is a plus. So this is not giving out heat. So if I do the reaction that C plus 2s in coffee cup, I put C plus 2s in coffee cup and I allow them to react. The temperature is not going up. Temperature is dropping down. That plus means. Make sense? Everybody got that? If the temperature go up, we give the heat as a minus. If the temperature comes down, we give the heat as plus. So that's endothermic. So this is which one? I am doing it. C plus 2s is CS2 87.9. So this is plus 87.9. Look like that's also. I think I copied mistake there since I had C plus 2. Yeah, that's right. So the, now this is a plus number here. So I need to calculate how much heat would change if I do this reaction using this number. Yeah. So I arrange this number in such a way that this number and this equation in such a way that I get my equation like this. Yeah. So I start from here. So look here. So what do I need here? CS2 in the left side, right? CS2 in the left side. So where is CS2? CS2 here is in the right side, right? So I need to put that CS2 to the left side. Everybody got that? So I'm putting that CS2 to the left side, S2. Why I put this CS2 in the left side? Because in the main reaction where I need to find the heat change for this reaction, CS2 is in the left side. So I put that in the left side. Now I put C and 2S in the right side. So like that. So C plus 2S in the right side. So I change the position. So I take this way. I take this way. So if this is a plus, I need to change the sign of that also. Make sense? So this is plus here. Since I'm just changing the position left to right. So that number for me becomes minus 87.9. Make sense? So why I am doing this? I'm doing it because I want to make my CS2 toward the left side where I need to find that thing, right? So let's look another one here. CS2. CS2 I need in left side. What do I need in left side? Now I need oxygen in the left side, but carbon dioxide and sulfur dioxide in the right side. So sulfur dioxide is in the right side, carbon dioxide is in the right side. I'm good. So carbon dioxide. So this equation and this equation are good. So C plus O2. So C plus O2 gives CO2. CO2 there. So I didn't change the position here. So I'm not changing that negative sign there. Minus 393.5. Right. Now another one, sulfur dioxide. So where do I get this sulfur dioxide? In the right side. So sulfur dioxide is already in the right side. So I'm not changing this one also. Sulfur plus oxygen, sulfur dioxide, like this. And what is the amount of the heat I have there? Minus 296.8. Minus 296.8 kilojoule per mole, whatever. Now, from this three equations, I need to add, subtract, cut, whatever I want to do, and I need to get exactly like this. So CS2. CS2, this is good. So I don't do anything for that one. CS2 looks good. One CS2, one CS2. And look here, there is no carbon in this side, right? So I don't have carbon this side. So I try to cancel the carbon from two equations. So carbon one is here, another carbon is here. So this is left side, this is right side. So this one and this one, I can cancel. Just like the algebraically solving equation, yeah? I'm just trying to rearrange things so that I just want to have something that I need. Now carbon is gone. How about the other thing? So do I need sulfur in the left side? No, I don't need sulfur in the left side. So I need to cut this sulfur. But here you see that sulfur 1 here, sulfur are 2 here. Can I cut 2 sulfur and 1 sulfur? I cannot cut, right? So I need to multiply this equation by 2 so that I can cut 2 sulfur and 2 sulfur there. Make sense? So I'm going to multiply this equation with 2. And since I multiply here 2, here also I multiply by 2, and here should also be multiplying by 2, and I need to multiply this guy also 2. One equation cannot be multiplied by one number at one point. It needs to be multiplied by multiply to whole the equation. Make sense? So I multiply everywhere. Now, can I cancel this now? Yes. So this is in the left side, this is right side. So I can cancel this one and this one. What else? So I think I'm good. Now I'm going to add this one. So when I add this one, can I get the equation like that or not? Let's see. CS2 here. So CS2. I write CS2. And here is 1 O2, here is 2 O2. So plus 3 O2. 3 O2. And this side I have 2 SO2 plus CO2. Okay, CO2. So everything looks good now, right? So I got the equation. Now how about the here? Let's look here. So this one I need to multiply 296.8 first. So how much this number gives? So that is 296.8. So I think let's go there. It's already multiplied in the slide here. So that is when I multiply that 296.8 by 2, that is minus 593.6. So that is minus 593.6. minus 593.6. So this I just multiply and write it here. So you need to add this number, this number, this number. So minus this number, minus this minus. So all three minuses are plus, and that gives me 10 minus 1075 kilojoule. Make sense? It's just a trick to get sum, subtract, or whatever you want to do. Keep doing, keep trying until you get the desired equation. Yeah. So this is just by using this three number, I could come up with equation something like that, and I did the manipulation of this number there here, and so I got that number. So if I put CS2 and oxygen, so basically, so I put the CS2 in coffee cup calorimeter here, and dump a lot of oxygen there, and measure the temperature, and I measure the mass, and CT2 minus T1, and I get that number. Yeah, so like this. So I think we are almost done with this chapter. We are 1 minute back, so let's see. So this is one. So let's do another way. So there is another way of doing one example and how to calculate it. So sometimes like this equation is given. So calcium carbonate. So what is the heat change? So let's say calcium carbonate. Calcium carbonate is reacting to give calcium oxide and carbon dioxide. Calcium carbonate, calcium oxide plus carbon dioxide, right? So it is asking basically, so what is the heat change here? So what is the heat change? So delta H is what is the heat change? So meaning you put the coffee cup, you take the coffee cup calorimeter here and put some calcium carbonate here, put the thermometer, and calcium carbonate will decompose to give calcium oxide and carbon dioxide. Somehow you are decomposing calcium oxide into carbon dioxide, calcium carbonate into calcium oxide and carbon dioxide here. So at the beginning, maybe temperature was 20 degrees centigrade. When it is completely broken, maybe it is 30 degrees centigrade. Now you have the mass, you have the T2 minus T1. Now you have the specific heat capacity. You calculate that, and how much heat would you get there using Q equal to mCT2 minus, right? So that we need to find. Make sense? So that is one way. But we don't have to do this reaction. So you can just do theoretically if you have data something like this. So if you are making calcium carbonate somehow, you will be changing this much heat. If you are making calcium oxide, somehow you will get that much heat. If you make carbon dioxide somehow, another way you would get that much heat. So just using these three things here, I can calculate how much heat I would produce or absorb there by doing this equation, just theoretically. Yeah, I don't need to do experiment if I have the number like this. Make sense? So it's basically you are doing the heat change. So heat change basically would be heat change for products minus the heat change for reactants. So that would be the total heat change. Total heat change for this reaction. So how much is that? Heat change for product is this guy and this guy. So calcium oxide and carbon dioxide are product. So how much heat is there? So that is 1207.6. So no, that's a reactant. So we need to do the product first. Calcium oxide. So that's minus 635.1, right? Minus 635.1 here, 635.1 here, and